I am not interested in using 3D printing to do what we could do before. I'm interested in using it to do things we couldn't even conceive of before. My assessment of where we are in the 3D, with 3D printing and additive manufacturing in general, is a little less bullish than you heard, at least in the short term. And so if I was to have a scorecard of where we are today, I would say there's a number of problems. The first one is reliability. Failure rates for 3D printing are insanely high. It's ridiculous. I mean, for those of us who 3D print all the time, the idea that, you get up in the morning, and that's because it takes so much time, you get up in the morning and you go look, and there's that feeling of anxiety when you walk over to your 3D printer to see if it's actually successfully completed. That has to end. We have to be able to send things to the printer and know that they're going to print, and they're going to print exactly what we want, and we can visualize those ahead of time. How many of you have seen stuff that looks like that? Okay. Second thing is I still think the quality is too low. The resolution is not high enough. The quality of the finished parts is not good enough for many of the things that we would really like to be able to use 3D printing for. Speed. Okay, let's wake up there. Does anyone in the audience have a 3D printer that's fast enough? And not you guys over there, because it's not commercially available. So, and here's the problem with 3D printing, is that things go up as the cube. So if it takes me an hour to print something, and I want something that's twice as big, it takes not 2 hours, but it takes 8 hours. If I want something that's twice as big as that again, it doesn't take 16 hours, it takes 64 hours. Now we're talking about something that's 4 times larger, that takes almost 2.5 days to print. And this is one of the fundamental things, at least for some of the existing technologies, we're always going to be fighting against raising something to the third power. And that's a difficult barrier to overcome. Last one is materials. We've all seen better materials coming. We all can dream of some of the materials. Most of the materials that we can print with today are really not good enough for what we really want to use them for. That's what happens to a lot of my parts when I put them into use. And I would make a slightly different assessment. I would say the hype is at its peak. It's been talked about to the point where I think many of the people who are going out and buying 3D printers are actually disappointed. They get them home, they print 3 things, and then they don't know what to do next. The tool chain and the workflow between tools is still too difficult. This comes from somebody who has owned dozens. If I kept every 3D printer I owned at some point, I would have a museum of 3D printers. Right now, all the high schools in my neighborhood are lucky because I use them for about a month and then decide that they're just not that useful. And I'm a guy who collects tools. There's barely a tool in the world that I have that I've given away because I like tools and I know what they can do. And to date, there's yet to be a 3D printer that I really wanted to own and wasn't willing to part with. But I think it's going to change. And though my assessment is a lot more dour than the others, I still think there's room for opportunity. As a matter of fact, why'd you guys invite me to keynote this thing? Given that I'm such a pessimist on particularly consumer 3D printing. But if you think about it, I think every one of the things that I've spoken about actually is an opportunity to do better. Every one of the things, if it's more reliable, higher quality, faster printing, is a commercial opportunity for someone to do better. And there are literally hundreds, if not thousands of companies and smart people out there trying to build better 3D printers. The one thing I wanted to talk about in the hype cycle that really is the one that I've spent a lot of time pondering, and I'm not at all clear that I have the right answer, but I'll venture an opinion, which is the idea that there's going to be a 3D printer in everybody's house seems a little far-fetched to me. Now, I would say something different. I think every one of us 3 years, maybe 5 years, will absolutely own things that have been 3D printed. But the idea that you're going to have a 3D printer doesn't seem that likely. For someone who's had a 3D printer in his house, and all my family ever says to me is, can you get that thing out of here? Because remember, it runs for 12 hours at a time, and it goes back and forth all night long. So the only thing I can do is cover it with a box. And then I take the box, and then I put a blanket over it. And then it starts to overheat, so I drill holes in the box to try to cool it off. This is not a home device. And if you contrast it with the toaster, which also is, you know, a modestly priced appliance with a low duty cycle, the reason why I think we all own toasters and are willing to dedicate space compared to 3D printers is I think the alternative for toast is lousy. So if I was to have to order one online and get my toast delivered 15 minutes, 2 hours, 2 days later, I don't think the toast is very interesting. But getting a 3D print from a company that's down the street, that is a FedEx or UPS away, that's actually an interesting business proposition, which is, I believe, how many of us will get our 3D printed parts. We'll see. Everyone's, you know, free to bet as they will on that proposition. But I find it a little bit far-fetched to think that we will all have them in our homes. So as you think about this, you know, you saw, I'm not that enthusiastic about where we are with 3D printing as a consumer activity. But I really do believe the work that I see going on with all the startups, with the big industrial giants entering the market, that's another one entering the market. They're calling you guys to report on it. I think is actually incredible. And I think the pace of innovation, while it has sped up considerably in the last 5 years, is going to continue at an exponential rate to increase, and we will see more dramatic improvements over the next 5 years than we've seen in the last 5 years. One of the places where I really do think consumer 3D printing is interesting is in schools. So one of the places where I think it's made a tremendous difference is in schools, particularly as schools have tried to revamp their education. You know, I'm fond of saying that certainly in the American school system, we're often, it often seems to me that we're educating our children for a future that no longer exists. You know, it's an education system based on the idea of we're going to take an agrarian population and move it into factories. That is not the world of our future. That's not the world of our children. The world of our children needs to be one that's filled with, you know, wonder and excitement and tap into their creativity and imagination. And I think the placement of 3D printers in schools has really helped with an equal emphasis in the curriculum on science and technology and engineering and math. One of the things that we've done that I'm most proud of, in the last year Autodesk made a decision just because of those things, is that we've decided to give all of our professional software, any piece of software we make, free to any student, to any school, or any teacher anywhere in the world. And it's because I have such a strong belief in the power of what our kids can actually accomplish. I think the best thing that we were able to do is just to arm them with the tools to tap into the creativity they already possess. Actually, this is me in my workshop. This is with a group of girls. A friend of mine named Emily Pilladin is, she teaches in a Berkeley public school in a low-income neighborhood, and she teaches a design and building class. And she runs it during the school year, and she runs it during the summer program. And she teaches lots of middle school students, and particularly a lot of girls, how to use CNC tools, how to 3D print, how to design, how to build. And one of the great quotes that came out after the end of the class was from one of the kids who said, "I'm a 10-year-old girl. I know how to weld. What can't I do?" And I think that sense of empowerment of kids being able to learn that they can design things, that they can solve problems, that they can change things, is incredibly empowering. Here's another example. This is at Maker Faire. And one of the things that I think we all risk doing is underestimating what the kids are capable of. I have been totally amazed by the middle schools in my area and watching what happens when you arm them with the tools, what kids are really capable of. You know, the digital natives have grown up in a different world and they're far more comfortable than we ever will be with these tools and what's possible. And probably the greatest thing about them is they seem to have no fear and are willing to try and willing to make mistakes and willing to do it over and over again. But the thing where I think the most commercial promise in 3D printing is in industrial additive manufacturing. And so let me talk a little bit about industrial manufacturing and why I think it has such a great potential to change the world. The first one is that shape complexity is free with 3D printing. Here's an example. This is a bowl I designed, I don't know, maybe 3-4 years ago, something like that. What was interesting to me was I actually tried to make it. I had 3D printed it first out of plastic, but I didn't want the final product to be plastic. I wanted it out of different materials. And in particular, I tried to make it out of metal. I tried at least 5 different techniques: casting and water jetting, just casting, wire EDM. I tried milling it, almost everything, and it was not possible. It was too complicated a shape for each one of the techniques for a different reason. But here's something where you could go right from CAD to a finished thing. This was printed in metal. It was printed in stainless and bronze, and came out perfectly. And I love this idea that my 3D printer couldn't care less whether I'm just printing a big block of, a big cube or something incredibly complex. And I think that's one of the reasons why we're all willing to put up with the shortcomings of what we see in 3D printing is that fact. The second thing that's driving everyone to do it is the fact that relatively little skill is actually needed. If I want to run a CNC mill, pretty difficult. If I want to run a bronze foundry, huge amount of capital investment, difficult to do, lots of know-how. All we need with 3D printing is a little bit of digital craftsmanship. It's a little bit of moving files from here to there, a little bit of knowing about supports, and even all of that needs to go away in the next few years. So I think this combination of shape complexity coming for free, plus the idea that little craftsmanship is needed, is what has captured people's imagination. So if we go back in time, and the first 3D printer I saw was probably 25 plus years ago. Back when everybody labeled the industry rapid prototyping, that to this point is still what I see as the greatest use of 3D printing. The most widespread use I see amongst our industrial customers is still as a rapid prototyping tool. And it's incredibly useful. As realistic as the images have gotten on the screen, as realistic as the models are, there's something different about putting it in your hand, about having a tangible object that you can put in your hand and fit to other objects and see what it looks like and roll it around and kind of feel the surface. There's just something different about it. And when we put it in place, it's great. But what's going to make these things that today are mostly prototype into objects that we can use more completely? So here's a great new printer. This is the latest in my collection. This is the Mark Forge printer. And what I think is really exciting about it is the quality of the materials that are coming out of it. So it's a printer that will print plastic, but reinforced with strands of either Kevlar or carbon fiber. And the parts that come out of it are much stronger. I think the team from Mark Forge is actually here. They may even be speaking. If not, I think they're upstairs. And you can see the parts. One of my colleagues, who is way braver than I am when climbing this weekend in Tahoe, he designed and printed that carabiner on the printer. It's plastic and Kevlar. So I would have thought it was bullet resistant or bulletproof. I'm not sure I would have actually hung myself from that. But he actually went climbing with that. He went climbing with that carabiner. So really interesting that all of a sudden we're starting to have things that are really not just prototypes, They're not just intermediate artifacts. They're the real thing that can actually do the job. One of the places where I think we're going to see the most of this is in places like in industrial tooling and fixtures. This is just an example. We do a lot of work with companies who do injection molding of plastic parts. And one of the things that limits injection molding, while very cheap, one of the limiting factors is how quickly you can cool it. And so this is just an example of being able to add conforming cooling channels to the molds in order to be able to cool it faster. The faster that you cool it, the more rapidly that you can produce parts. Okay, one of the other things that's changed is software. I just want to talk a little bit about a new product that we introduced. It was called Fusion 360. And it's the first cloud-based mechanical CAD system out there. Like our other stuff, it is free. We've also made it available to not only the students in universities, but to enthusiasts, people who want to print. And one of the things that I think is particularly interesting about it is it combines what is traditionally the domain of mechanical modeling, which is prismatic parts, with the world of industrial design with much more organic shapes. The interesting thing about many of those organic shapes is they're fairly difficult to produce in low volume. And that's really one of the big tricks in my mind about 3D printing, is that if you look back at the Industrial Revolution, what happened in the Industrial Revolution is we got high quality and low cost by making thousands of things, thousands of identical things. What's interesting about 3D printing in the whole new world of digital fabrication is that we're starting to be able to get that same level of quality at the same cost, but in very small numbers. And so what was interesting is being able to have a product that is able to design things that are ideally fabricated using 3D printing. So this is just an example of some of those parts. This is just some of the things that were designed in it. But what was particularly interesting to me was the idea that from the beginning, the tool was built with a workflow that imagined 3D printing as the output. So as opposed to the tool chains now, which are a little bit convoluted for anyone who's ever done it, this was some of the spark, if you will, for the idea of how we're going to tie together our design and modeling tools with how we're going to make things eventually be printed. Now let me move on and go to this idea of generative design. In order to understand Autodesk's involvement in 3D printing, this is probably the best insight I can give you. You know, we sat down a number of years ago and started to think about what the future of design and engineering would look like. And despite, you know, having personally spent several decades around what was labeled CAD software, you know, 3D modeling or CAD software, I really didn't think that our computer-aided design software really enabled the computer to do much aiding of the design. What the computer mostly did was document our design. You know, if you think about how you use most 3D modeling tools today, you already have an idea in your mind and you're asking the computer to record what's already in your mind. And so the question to me was, given the advances in computing technology, processing, bandwidth, memory, what was going on, what would it look like? And so we spent a lot of time thinking about it, and one of the big conclusions we came to is that for most of the years that we've been using computers in engineering, we've treated computing as a scarce resource, as something very precious. We time-shared it. You know, we doled it out. And if you look today, what we saw was the price of computing was falling. It was falling in a predictable way. The trend was going to continue. And not only were the prices getting so low that, for example, I can rent a CPU hour for less than a nickel. I can get as many CPU hours practically as I can put to use. I can rent 1,000 or 10,000 or 100,000 CPUs. And so this idea of the price point approaching zero and the widespread availability of CPU cores led us to think, how would you design differently if you had infinite computing? So what would you do differently? And so the first thing we said is, okay, what is the process of design? Very often today, people design things, and then they digitally test it, and then they physically test it. And it reminds me a little bit of the game of Battleship. Remember that game? Where the engineer goes B2, and the analyst says miss. And then the engineer says J5, and the analyst says miss. And you go through iteration after iteration trying to find a suitable design. And eventually you run out of time or patience or money, or you just accept good enough, and then you move on from there. And I thought we can do better than this. And so the first thing we started to do was to run lots of simulations in parallel, saying rather than make this a serial process, why don't we make it a parallel process? Rather than asking the question one at a time, why don't we ask it over some domain, some range, some space? And the computer is really good at these brute force techniques. And so exploring a multivariate space is a reasonable thing to ask a computer to do. It blindly goes and does it, and it comes back and it finds an optimal or near optimal answer. And so we started to build on this idea, and we said, okay, so now if I wanted to talk to the computer, rather than in the low language of explicitly drawing geometry and explaining the constraints, what way would I talk to the computer to explain what I want to design? How am I going to express this? And so we've been working on this for a while, and I'll show you how this idea of generative design leads to our keen interest in additive manufacturing. So this is an example of a heat exchanger. It was designed entirely by the computer. The specification of the requirements, the thermodynamic properties that were needed, were described to the computer, and the computer generated this design. So interesting, nobody sat there and said, I want that curve and it looks like some kind of muted sinusoidal curve. Nobody said this. They described high-level description of the problem. So let me show you in a little more detail. So this is another heat exchanger that was designed. And what you do is you basically specify some of the high-level constraints. For example, in this case, it needs to fill a space envelope this big. Here's the cube of material that you have to work with. Fluid's going to come in one side, fluid has to go out another side. There are some thermodynamic properties that we want to meet. The computer explores thousands, tens of thousands, hundreds of thousands of different options. Here's one of the options along the way. Here's the finished heat exchanger. Again, this is a heat exchanger that was designed entirely by the computer to some degree. And what I mean by that, the specification of it was entirely done by the engineer. What was required to solve the engineering problem was done by the engineer. The geometry and topology of it was actually created by the computer. What's interesting about this to us is we started to see lots of examples where, in fact, the computer could design a better product. It was lighter, it performed better, and it was stronger. So it met all of the traditional criteria except for one. That thing is very difficult to fabricate using traditional techniques. And over again, the shapes we were getting were there. And so we started looking at the criteria to expand to how could you include manufacturability, not just the geometry, topology, and other engineering characteristics, but what could you do to make sure that it was manufacturable? And there's no limitation on that being one of the inputs to the process. So interesting that you get what I think is a beautiful heat exchanger, but also one that performs better. Here's another example of some of the forms that are actually generated by the computer in response to different conditions. So, you know, a typical kind of problem that we're working on with these optimization techniques is, for example, let's take a typical engineering problem. You have a bracket. It needs to have a couple of mounting holes. It needs to fill a space envelope, needs to support certain loads. Rather than doing that rather mundane engineering task, why don't we really start having computer-aided design and let the computer help us design those kinds of brackets? And so this is another example. We're also doing some work with Airbus. So we started to work with Airbus because one of the things that became really interesting to me about additive manufacturing in an industrial context was the idea that at any point in space, that at any voxel, I can essentially put any material I want. So rather than taking a technique where you take standard materials off the shelf, we are approaching a world in which we can custom design materials for the specific task at hand. So rather than just grabbing aircraft-grade aluminum, we can make up materials that are a mixture of the appropriate materials. And at every point in space, and you see this already with the printers that do multiple materials, and this is going to continue, where I believe we will have bespoke materials for the thing we want, rather than trying to figure out how we're going to transform stock materials into the object that we want. So this was work we did with Airbus, trying to imagine an aircraft of the future. So of course they wanted more comfortable, they wanted it lighter, they wanted it stronger, and they wanted it more fuel efficient. And so this is some of the work we did with that algorithmic design to look at the aircraft of the future. And here's a view of what it looks like inside. Here's another thing. Here's another one. This is a work we did with a company called Moon Express. Moon Express is building a lunar lander. They're working at NASA Ames in California, and they want to land, this little vehicle on the moon. One of the things they did in designing their lunar lander was this really interesting design in which it's a torus-shaped fuel tank. And what they did is they made a torus-shaped fuel tank that's made out of carbon fiber with an inflatable bladder. And the idea was to try to balance out the fuel naturally by having the inflatable bladder. It automatically balances. Oftentimes, as we all know, when you solve one engineering problem, you create another. So the interesting one in this is the surface on the right represents that torus-shaped fuel tank. The one on the left is the mounting bracket, where they now have to mount a rocket thruster to this torus-shaped thing. What they wanted was the strongest, lightest way they could to attach the rocket thruster to there. And so as opposed to some of the other algorithms, this is a different one in which we're actually growing material, thousands of different options, in order to achieve the engineering specification for the weight and the strength of that bracket. So another approach to go at to generate, again, very interesting shapes, and once again, the only way that I know to fabricate these will be to 3D print them. Here's a slightly more terrestrial example. This is Lightning Motorcycles. Lightning Motorcycles has broken the land speed record for production motorcycles at 218 miles an hour out at Bonneville. And they were interested in pushing that a little further. And so they were looking at how could they make the swing arm for a stronger suspension and a little bit lighter. And so we did some work with them on the carbon swing arm that they were looking at. As a matter of fact, that picture I showed you in the beginning was one of the prototypes of the swing arm. We had some successes, but we also had some macaroni and cheese. What's interesting here is the image on your left is a computer-generated version of the swing arm. The other two things in there, does anyone know what they are? Yeah. It's a cat pelvis. And we never asked the computer to design a cat pelvis. What we actually asked it to design was a swing arm. And one of the really interesting things about it, if you look closely, if you look on the right side, there's a hole in the left side, and so it's a fairly symmetrical swing arm that the computer designed, with the exception of there's less material on this side. Any of the engineers in the audience know why? Because motorcycle has a chain, and all the force is applied on one side, and so there's actually asymmetrical loading of the swing arm, whereas the cat is symmetrical loading from an engineering point of view. So anyhow, another interesting design that was computer generated. Here you can see it actually evolving the design. So started with the big envelope, and you can watch over time This is sped up considerably, but we're doing lots of iterations per second and testing with a fitness function to see which best solves the problem, and we're evolving to designs that look like that. Here's another interesting one. This is the growing of metallic. It's a foam-like structure. And the part here is a hip cup. And once again, this was designed generatively. It was designed algorithmically. And what it's intended to do is perform the engineering function of replacing the hip cup, but most importantly, that foam-like structure is actually a carefully engineered metal lattice. And in particular, what it has is a random pore size. And the random pore size is clinically demonstrable to be better at mimicking to the body that it's weak bone. And so the bone metal integration, the osseo integration, is much better in a piece like this than it would be if it was the same pore size. Now let me move on and talk a little bit about what Autodesk is actually doing. In some ways, hopefully the generative design gives you some insight into what has made us so interested in this idea of 3D printing. And in particular, what we see, in order to have 3D printing realize its full potential, we see a world in which software, hardware, and materials need to all improve and need to work better together. So the first thing we did, we announced the Spark program, which is an open software platform for us and everyone else in the industry who wants to participate in it to have a foundational level of software that deals with the idiosyncrasies of each machine and of the tools that feed them in order to get to a level where many of the mundane problems that we all experience today disappear. And so we're working together with a number of really great partners on Spark. Here are some of the partners who have already signed up with Spark. One of the ones is HP. Very excited about their announcement. I'm sure all of you followed. They've talked about a printer that's 10 times faster and costs half as much as the existing models out there. Like I said, I may be a little bit down in the dumps about where we are today, but I think there's really exciting things coming on the horizon. Having a machine that's 10 times faster is starting to be the kind of machine that I want to keep around in my shop. So I'm very excited about working with companies like HP and building a community of people who all want to contribute. I think there was a reference before. I think this industry has been plagued by short-sightedness and small-mindedness around intellectual property protection. And I think there's a better way forward for the whole community in which we can all do much better by growing the pie rather than fighting over tiny slices. Here's another one. This is Shapeways, and I think Peter's going to be here today. He may be following me. I am a huge fan of Shapeways and a loyal customer. Actually, my metal bowls were all printed by Shapeways. And I think this is one of the ways in which you will have custom-made objects that are actually printed by people like Shapeways, and even some standard objects that are manufactured just in time by companies like Shapeways. And so I think it's a fascinating way that we will all enjoy the fruits of 3D printing, regardless of whether we actually own 3D printers ourselves. There's another one of the partners, Local Motors. Sorry, it's a little washed out here, but this is one of the cars many of you have watched as they've been 3D printing cars, totally customizable. Very excited about starting to see 3D printing go large scale. This is another one of the partners, and this is Nervous Systems. Jessica and the team, I think, is doing awesome stuff there. I love the work they're doing. Dress doesn't look so good on me, but lots of the other stuff, I really like what Jessica's doing. And I believe this is actually a dress that's now available and printed by Shapeways. So some fantastic algorithmic design, some fantastic design work being done there, and really pushing and probably one of the best examples of what I talked about, of not taking new technology and just doing the same old stuff. This is taking new technology and doing something really different. Okay, the other thing that we announced this year is a Spark investment fund. So this is for entrepreneurs and startups and researchers who are working in the world of 3D printing. We announced a $100 million fund. We've started to make investments in companies, and we continue to be oversubscribed in terms of the number of applications. But I encourage anyone with good ideas who's looking for funding for them to apply to it. The other thing we announced was the Ember printer. There were some references to it earlier. So our Ember printer, this is a SLA machine with a DLP. What's interesting about it to us is we built it as a reference implementation for Spark. We wanted to have a machine out there so that we could demonstrate what could be done when hardware, software, and materials all work together. So just like Spark, which is open software, Ember is open hardware. We will be publishing the plans for the Ember printer. Anybody who wants to build their own can. Anyone who wants to hack it can. And the last part of it is we really want it as a platform for experimentation around materials. And so it's open materials. We'll publish the specs for it. You are free to put in whatever you want. And so we'll have open hardware, open software, open materials. And I think that's really the power of the three things coming together. Here's one of the outputs from the Ember printer. It's printing in the XY direction at the resolution of tens of microns. So if you look at that, you can see there's the pencil point, and it looks like we're printing toothbrushes or combs or something like that. So really interesting, but the most interesting thing to me is not the specific machine. It's the combination of a platform where software, hardware, and materials come together. If you want to get on the waiting list for it, they're starting to ship this month. That's where you sign up for it. If you want to just see it and play with it, it's upstairs. Let me just take 1 minute here at the end, talk about some of the things that I think are really exciting that are coming in the way of 3D printing and bring me out from those doldrums that I started out in of why this was so lousy and why it's going to be so good. Here's an exciting company. There's a number of them out there. This is Cambrian Genomics. They're actually 3D printing DNA. First time I went in there, it absolutely blew my mind. I walked in, guy starts describing what's the printer doing and blah, blah, and I'm like, slow down, I'm not that smart. Finally I said to him, okay, those 4 tubes, what's in the 4 tubes? And he says, A, T, C, and G. They are literally printing 3D printing DNA. And through a combination of mechanical engineering, image processing, microfluidics, they can reliably produce relatively long strands of DNA. The day of mail ordering DNA is coming. So a friend said to me, he texted me the other day, a friend who's worked in alternative energy for a long time, texted me, he was watching some presentation, he said, I'm no longer scared about global warming. I thought, for my energy friend, why would that be? And so I wrote back, why? He said, I'm terrified about some kid hacking DNA in his bedroom. We're not going to get to die from climate change. We're all going to die from a virus that's created by an 18-year-old. Anyhow, exciting stuff coming with DNA. This is a project that we're doing to explore putting conduit and empty volumes to be able to run things like electronics through 3D printing. This is work that'll be coming out. Most likely you'll see it in places like the Spark platform. Here's another one that's really exciting. This work we're doing is a project called Wire. This is with a company called Voxelate. You can see it upstairs. So this is a combination of printing plastic and conductive material. You can see the placement of some of the electrical components. Okay, so printing plastic and electronics. I think this is the beginning of an era of really much more complete products than ones that are just about the geometry. This is another great project. I love what this is doing. This is Achim Menges at the University of Stuttgart. He's been using industrial robots to do wet layup of things like carbon fiber. He's been building architectural size structures. There's one of them. So just think about this. Actually building architectural scale structures out of carbon fiber, essentially 3D printing them. So again, novel uses of new technology. Here's one that really has me exciting. This is the combination of additive and subtractive. This is some work being done by our Delcam group in the UK. And this is combining the idea of we're going to do additive printing. So we're going to add metal, and then we're going to mill it. What you get is the material efficiency that comes from 3D printing and the precision that comes from subtractive techniques like CNC machining. And then the last thing here, oh, there it is. There's the laying up, and then you'll see the trimming. Let me just move on because we're getting to the end. This is some work we're doing with an artist in Amsterdam named Joris Larman, and he's using, again, industrial robots to, some people would say 3D print, others would say MIG weld, but he's laying up metal in space. So he's drawing out curves, and then the machines are printing them. Here's some of the structures that Joris has done. Here's the final image. This is a project we're working on with him for Amsterdam, in which it is a generatively designed bridge that will be autonomously built by the robots. So, interesting combination of robotic fabrication along with generative design. And that's why I'm excited about the future. Thanks.